All right, guys, before we get into note card 22, I just want to talk about the graphs of our six basic trig functions. And those six basic trig functions are sine, cosine, tangent, cosecant, secant, and cotangent. All right, so what I did here first off is I drew in red here, this is a cosine curve. Okay, and in green, that's a sine curve. And if you're unsure what those look like, you can just use values from the unit circle to plot them out. Okay, so what does the graph of tangent of x look like? Well, if you remember the basic rule that tangent is always the sine value divided by the cosine value, that's going to help you out. So if you think about it, remember sine is in green and cosine is in red there. So, for example here, okay, at 0 degrees, the sine is 0, but the cosine is 1. So what would 0 over 1 be? Well, it would be 0. So the tangent of 0 is 0. Okay. Now what happens between 0 and 90? Well, the sine values are going up, they're increasing, but the cosine values are going down. So the numerator is getting bigger and the denominator is getting smaller. What's going to happen to the y values there? Well, as this gets bigger and this gets smaller and smaller and smaller, the fraction becomes bigger for every degree. Okay, so it's going to start to increase. Okay, the tangent values increase between 0 and 90. And even at 90, okay, at 90 degrees, the cosine is 0. You're not allowed to divide by 0. So what that does is it creates a vertical asymptote in the graph. But between 0 and 90, it goes up. Okay? And actually, exactly at 45 degrees, the values are the same. Okay, so right at 45 degrees, the tangent would be 1. But after 45 degrees, goes up towards infinity. Now what about between 0 and negative 90? Okay. Between 0 and negative 90, all the cosine values are positive, but all the sine values are negative. So we would be getting negatives over positives, which would make it negative. Okay. So what's going to happen down here is, and again at negative 90, the cosine is 0 again, so it's going to create another vertical asymptote. Okay, so what's actually going to happen on the graph, if you plugged in different degree measures each time, at negative 45 degrees, one is positive radical 2 over 2, the other is negative radical 2 over 2. So that's going to give a value of negative 1 at 45 degrees. Okay, and then it's going to go like that. So a tangent function kind of has that shape between negative 90 and 90. And then what you'll notice, if you kept going and putting the sine numbers and dividing them by the cosine numbers, every time the cosine is equal to 0, you're going to get an asymptote. But this pattern is just going to repeat and repeat and repeat over and over and over. Okay, it's going to repeat over and over and over. Every time the sine value is 0, the whole fraction is 0. So this is what a tangent graph looks like. All right. And on this side, it's going to go up towards infinity. So that's how we get the tangent curve. We take our sine values and we divide them by our cosine values. And you get the same pattern, and starting at 90 degrees, you get a vertical asymptote every 180 after that. Okay, or every 180 less than that. Okay. Now, how do you draw a secant curve? Okay, let's think about this. Okay. The secant is the reciprocal to the cosine. So what I did on this one, I drew in a cosine curve in red, just like I did up in the first example. Okay. Now, if you take at this value, at this exact value at 0 degrees, the cosine equals 1. Okay, so what would 1 divided by 1 be? It would be 1. But what happens when the cosine, what happens when this denominator is 0, such at 90, at 270, at negative 90, at negative 270? You're not allowed to divide by 0. So whenever that red dot is on top of the x-axis, you're going to get a vertical asymptote for the secant graph. So you'll get a vertical asymptote there, you'll get a vertical asymptote there, you'll get a vertical asymptote here at negative 90, and you'll get a vertical asymptote at negative 270. Okay. But what's happening here? What's happening right here? The cosine values, they're getting smaller. Okay. So each time, for every 1 degree you move further and further over between 0 and 90 degrees, the denominator is getting smaller. What does that mean about the whole fraction? 1 divided by a smaller number is going to be a number bigger than 1. So what's going to happen as you get closer and closer and closer to 90, it's going to go up towards infinity. For instance, like right here, maybe the y value is 0.01. What would 1 divided by 0.01 be? It would be 100. So this goes up really quick. And same on this other side. The y values are getting smaller and smaller and smaller for cosine, so all of these values get smaller and smaller and smaller, which makes the whole fraction bigger and bigger and bigger. Okay, so that's the beginning part of the secant graph. Now, what about at 180 degrees? At 180 degrees, the cosine value is negative 1. Well, what's 1 divided by negative 1? It's negative 1 as well. Okay. And the closer I get to this value, my y values are getting closer to 0. So you're having 1 divided by a negative number that's getting smaller and smaller and smaller. That means the whole fraction is becoming more and more and more negative. The magnitude's getting bigger and bigger and bigger, so that heads down towards negative infinity. Okay, and on the other side, kind of does the same thing. There's some symmetry there. All right, so this secant graph, if you kept doing this over and over and over, you basically get a whole bunch of u's. Okay, you get alternating u's. You have like one go up, then you'll have one go down. Then the next part will go up, and then if you kept going, the next part would go down. Over here, it would be going down. Okay, so basically secants, the secant of an angle is always a number that's bigger than 1 or smaller than negative 1, or equal to 1 or equal to negative 1. Over here, it would be going up. Okay, so it's an alternating U pattern. That's what the graph of secant looks like. Okay, so whenever I have a hard time remembering what these graphs look like, I draw in the original function like cosine, and I know that secant is the reciprocal function to that. Okay, so just like the tangent curve, the secant curve has asymptotes at the same degree measures. And remember, I gave these in degree measures, but I could give them in radian measures. All right, now so we've covered sine, we've covered cosine, we've covered tangent, we've covered secant. We've got 2 more to cover. Okay. So, in this next one, here's the sine curve in green. Let's think about what the cosecant curve would look like. Cosecant is the reciprocal of sine. Okay, so it's very much like the secant curve, which is the reciprocal of cosine. Kind of does the same type of thing. So you know when you're dividing, this can never be 0. If that equals 0, it's going to create an asymptote. So where is the sine equal to 0? Well, where does it hit the x-axis? Right there. So we would get a vertical asymptote there. At 180, we would get a vertical asymptote for our cosecant graph. And at 360, we would get a vertical asymptote. And we would get one at negative 180. There'd be a vertical asymptote. And at negative 360. Okay, and then it kind of does the same thing as what secant does. Here the sine value is 1, so 1 over 1 is still 1. As you go towards 0, the y values get smaller. That means that this fraction would actually get larger, closer and closer and closer to infinity. And the same thing on the other side. Here the sine value is negative 1, and as I get closer to 180, it gets closer to 0, so the magnitude of this gets bigger even though it's negative. So more U-shapes. Same thing over here. More U-shapes. So this graph in red that I'm drawing now, this is the graph of cosecant. So alternating U's. One goes above, one goes below, and you have asymptotes every 180 degrees. Okay, starting at 0, add 180, add 180. Starting at 0, subtract 180, subtract 180. That's where the asymptotes are going to be. So cosecants can only take the value 1 and greater and negative 1 and smaller. Okay, the last graph we're going to talk about is the cotangent graph. Cotangent is the reciprocal of tangent, but I can write tangent as sine over cosine. So 1 divided by sine over cosine is actually going to be cosine over sine. So cotangent equals the cosine over sine. Well, what about 0 degrees? At 0 degrees, the sine is 0. Okay? So at 0 degrees, sine of 0 degrees equals 0. Well, I'm not allowed to divide by 0. So what that does is it creates a vertical asymptote at 0. What about at 180 degrees? Sine of 180, if you think about your unit circle, there's no vertical component, so that's also 0. So we're going to get another vertical asymptote at 180. Then if you keep doing it, we would get one at 360. We would get one at negative 180. We would get one at negative 360. Now, let's think about this for a second. What would be true at 90 degrees? Okay, if you plugged in 90 degrees here and here, well, cosine of 90 is 0. Sine of 90 is 1. 0 divided by 1 is 0. Okay. All right. So what's true between 0 and 90 degrees? The first quadrant of the unit circle. Both of these things are positive there. So cosine of any number between 0 and 90 is positive. Sine of any number between 0 and 90 degrees is also positive. So a positive divided by positive is positive. Now what happens as you go from 0 to 90 degrees? Cosine starts getting smaller and sine starts getting bigger if you go back to the cosine and sine curves. So this fraction starts out really, really big because the cosine starts at 1 and sine starts at 0. Okay, so the number starts really big, but as we keep moving, it gets smaller and smaller and smaller. Okay, so the graph's going to start to look like that. As you go, the fraction is going to get smaller and smaller and smaller. Okay, and then when you move to the second quadrant, numbers between 90 and 180, okay, the cosine in the second quadrant is negative, but the sine's positive. So you get negative over positive numbers, which are negative. So when we graph, if you plotted out all the points, they're going to be negative. It's going to start to look like that. Okay. Then every 180 degrees it actually follows the same pattern. So it's going to follow that exact same pattern for the rest of the graph. And every time it crosses the axis right here, those are the angles, those are the degree measures where the cosine equals 0. Every vertical asymptote happens when the denominator would equal 0. So that's what the cotangent graph looks like. So that was just kind of a review of what the graphs themselves look like. If you know what the sine and the cosine graph look like, you can generate the other 4 graphs here. Okay. You can also put them into your calculator. Now let's start talking about derivatives. Okay, let's go to the actual note card. I'm going to write it a little bit differently though. So we've already talked about the first 2. All right. We should know already that the derivative of sine, and I can just write it like that, the derivative of sine equals cosine. Shouldn't have any problem with that. We also said that the derivative of cosine equals negative sine. Now, just for simplicity, I'm going to write the other ones in here. Okay. So there's actually 4 other trig functions, right? So we have a derivative of tangent, and I'll write that in just a second. I'll tell you what that is. We have a derivative of cotangent. There's a derivative for secant, and there's a derivative for cosecant. I'm going to tell you what they are, and I'm going to try to explain why they are what they are. Okay. So the derivative of tangent is actually secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant of x tangent of x. And the derivative of cosecant is actually negative cosecant of x cotangent of x. You do need to memorize these and you have to know them well. There is kind of a pattern here, if you can see it. For every trig function that starts with c, cosine, cotangent, and cosecant, their derivatives are all negative. Hopefully you see the negative in front of those 3. Okay. For every trig function that doesn't start with c, sine, tangent, and secant, all their derivatives are, there's an understood plus in front of there. They're positive. Okay, there's not a negative in front of them like these 3. Okay. So, okay, we already talked about why the derivative of sine is cosine, and we already talked about why the derivative of cosine is negative sine. We did that, I believe, in note card 16. Now I kind of want to show you why the derivative of tangent is secant squared. So what I'm going to do here, without having to redraw all of this in here, okay, let me just put in tangent of x here. And then I'll do a zoom trig. So there's our tangent curve coming up right here in green. Okay. If you think about it, if I drew in a little tangent line here, actually let's kind of narrow it down. Let me just go between negative pi and pi. Okay. So here's just part of the tangent curve. So let's just look at part of it so we don't confuse ourselves. If you were to draw in little tangent lines here, right at 0, the slope would be 1. And what do you notice about the slopes? If I drew in a tangent line right here, that line's really steep. So it starts out with a really steep line, And every time I draw on a tangent line, it gets a little bit less steep until I get to 0. But they're all positive. And then when I go from 0 to 90 degrees, I draw in more tangent lines. They're starting to get a little steeper, but they're all positive. So the derivative values, the slopes of the tangent lines, are always positive, has a minimum slope of 1. It never gets less steep than 1. And then it gets smaller on this side and bigger on this side. And it does that every time. So if I go ahead, I'm just going to type in secant squared here. Now how do I type in secant? I actually do 1 over cosine. This is the only way you can do secant. 1 over cosine squared. So that's the derivative. So if I graph in the derivative there, okay, if I were to plot all the slopes, think about why that's the derivative. Okay, because the slopes are getting smaller but staying positive, and then they start to get bigger. So you get these u's, but they're always positive, okay, because the slopes of the tangent lines of tangent would always be positive. And that's why on this one, if you think about the cotangent curve, how do I type in cotangent here? Let me get rid of these two. Okay, let's think about the cotangent curve. The way I type in the cotangent curve, there's no cotangent button. I just do cosine of x over sine of x. So here's the cotangent curve. Okay, think about the slopes, anywhere you drew on a tangent line. The tangent lines would always be going downward, so they have negative slopes. Okay. It hits -1 is actually the biggest negative slope. Okay. And then they get more negative. So if I go ahead and type in negative cosecant squared, okay, so I would do negative, here's how I would have to do it. Okay. Oops, negative, there's no cosecant button, but cosecant is 1 over sine. Okay, so that's how I would have to type in negative cosecant squared. If I graph that, think about why this graph coming up is the derivative function. Because if I drew in tangent lines right there, the tangent, the slope would be -1. If I go a little bit to the left and draw a tangent, it's a little bit steeper than -1, so it's a little bit more negative, and they're always negative. Cotangent always has negative slopes if I drew in tangent lines. Okay, so that covers tangent and cotangent. Now let's look back at the secant curve. Okay, because secant curve is kind of funny. Let me just do this in red. Okay, so if I want to draw a secant curve, the only way I can actually type in secant is to do 1 over cosine. And for this one, I'm going to go a little bit further. I'm going to go back to zoom trig so we can see more parts. Remember, this would be the alternating u's. Okay, so this is what secant looks like. It's the reciprocal to the cosine graph. And that's going from 0 to 360, 0 to -360. Here the slope changes all the time. So like right here at this exact value right there, it has a horizontal tangent. So at 0 degrees, the slope's 0. At -180, the slope's 0. At -270, the slope's 0. Okay, at positive, what's that? I guess these are every 90, right? So yeah, at 0, at 180, at 360, so on and so forth. Okay, so over this period, the slopes are positive and they're getting bigger. Okay, over this part, the slopes are negative and they're getting bigger. Over this part, the slopes are negative and they're getting smaller. And And then here, they're negative and getting bigger. Okay. So this is a secant graph. Y is the derivative of this secant tangent. Well, how would I type in secant tangent? Okay, well, I type in secant, so that's another 1 over cosine times tangent. Let's see what that looks like. Okay, here's what the derivative graph looks like. Kind of a crazy looking graph. Okay, just think about it point by point. Okay, so let me narrow this down a little bit. Let's just go from negative pi to pi instead of going that far out. Okay. So in red here, here's the secant graph. And what's coming up here, here's the derivative to that. Think about this first part in red. The tangent line slopes are negative and they're getting steeper. So all of the values of the derivative should be negative and they should be getting more negative. That's what this blue part does. And what's happening over this little part? Well, if I drew in tangent lines, little tangent lines, the slopes are all negative, but they're getting closer and closer and closer to a slope of 0. So they're negative, but they're approaching 0. Then on this part in red, the slopes are getting bigger and bigger and bigger, and they're being positive. So that's why that part of the graph looks like that. And this part, the slopes are positive. Okay, if you drew in tangent lines here, we would have positive slopes because it looks like they're going up. Okay, but they're getting less steep. Okay, so they're positive values, but they're decreasing. Okay, the slopes would be decreasing in value. So that's why the derivative is what it is. And now you're not going to have to prove why they are what they are, but on these 6 trig functions, you have got to memorize what the derivatives are. You've got to know those. Okay? You just have to know them. All right, so let's jump into some examples here. I know this video is long, and I apologize about that, but you got to know it. Okay, so I try to explain why the graphs look the way they do, but what's really important for this note card is know these derivatives. Okay? Know the derivatives for the 6 trig functions. All right, so let's do some examples here. All right, and up at the top here, we've already covered those. Those are the other 4. So we already had sine and cosine. These are the other 4. So it says if y equals the tangent of x minus the cotangent of x, then find the derivative. So how am I going to do that? This is a subtraction sign, so I'm going to take the derivative of that and then subtract the derivative for that. Derivative of tangent is secant squared minus the derivative of cotangent is negative cosecant squared. So if we simplify this a little bit, y prime, we could say that secant squared of x minus a negative turns into a plus. Okay, so this is an answer or anything that's trigonometrically equivalent to that. Okay. What do I mean when I say trigonometrically equivalent to that? For example, if that wasn't an answer choice, secant is 1 over cosine, so secant squared is 1 over cosine squared. Okay. Cosecant is 1 over sine, so cosecant squared is 1 over sine squared. So this is an equivalent answer. Or you could get a common denominator. Okay, so what you could do here for the first term, you could multiply by sine squared over sine squared, and you could get y prime equals sine squared of x over sine squared of x cosine squared of x, plus, in the second one, you could do cosine of x, cosine squared of x over cosine squared of x, and you would get cosine squared of x over sine squared of x cosine squared of x. And now you have a common denominator. So you get sine squared of x, cosine squared of x, and up here you have sine squared of x plus cosine squared of x. And you should know that sine squared plus cosine squared equals 1. So they could write the answer as 1 over sine squared of x cosine squared of x. So there's a lot of different ways they could write the answer. Now if it's free response, any one of these three answers could work. You could stop right there at the green. Okay. So let's think about problem 2 here. It says evaluate the limit as h approaches 0 of this thing minus this thing over h. Well, if you remember your definition of derivative, f prime of x equals the limit of f of x plus h, that's what that part is, minus f of x all over h. So what's important there? If you look at this part right here, that's what the function is. The function is 4 times the secant of x. What the question's really asking for is f prime. That's what it means by evaluate. So you don't have to go through the whole limit process, you just have to know what the derivative of secant of x is. Well, what's the derivative of secant of x? It's secant of x times the tangent of x. So there's my answer. So that is the correct answer, or anything that's equivalent to it. What do I mean by that? Well, secant's 1 over cosine, and tangent is sine over cosine. So if you think about this, 4 times 1 times sine is 4 sine of x, and 1 times cosine would be cosine squared. They might write the answer like this. These two things are exactly equivalent to each other. All right. So number 3, it says if a particle moving along the x-axis has this velocity, find the acceleration. Well, what do you know about acceleration? Acceleration is the derivative of velocity. But look at your velocity function. It's a quotient, so you have to use the quotient rule. So we say low, that's 5t, d high, so what's the derivative of the top? So the -6 would stay, times the derivative of cotangent. What's the derivative of cotangent? It's negative cosecant squared. Okay, and this is of t instead of x, because these are all t's. Okay, minus high -6 cotangent of t, d low, the derivative of 5t is just 5, all over low squared. The entire 5t gets squared. Okay. So if we simplify this a little bit, well, I have a -6 times another negative, negative's positive. All right, so I can basically cancel out these negatives. They're going to multiply and give me a positive. 5t times 6 is 30t. So I get 30t cosecant squared of t. Here you have -6 times 5 is -30, but then it's going to be minus a -30, which is going to turn into a plus 30. Plus 30 cotangent of t. And be really careful when you square the bottom. You got to square the 5, and you also have to square the t. So 5 squared is 25, and t squared is t squared. Okay. So if you do a little bit of simplification, I can pull out a 30 of the numerator, and I get t cosecant squared of t plus cotangent of t over 25t squared. You can reduce that. And you can divide both of those by 5, and you can get something like this. So you could say, final answer here, let me just write it again, 6, then in parentheses, t cosecant squared of t plus cotangent of t all over 5t squared. So your arithmetic simplification, your algebra simplification will be useful on the multiple choice portion. But if this is a free response, okay, if this is a free response question, and you don't have to go any further than this, then stop there. There's no use simplifying and losing possible points. Now, if it's a multiple choice question, this answer might not be there. That answer might not be there. That answer might not be there. That might be the answer that's there. So just know when you have to simplify versus when you can leave it alone. All right, number 4. Determine the point or points at which the horizontal tangents, okay, as soon as I see that, I'm going to say that's when the derivative equals 0 occur. Okay, and I want to find the points, which means I want to know the x and y values. Okay, on the graph of this over this interval. Okay, they gave me an interval because it's a trig function. Okay, so first thing, I need to figure out where y prime equals 0. Well, what's y prime going to equal? Well, what's the derivative of this thing? 2 times, what's the derivative of cosecant? It's negative cosecant of x cotangent of x. The derivative of a constant is 0. I don't have to go any more than that. So that's what the derivative function is. Y prime equals negative 2 cosecant of x cotangent of x. And if I wanted to do something that I know, instead of dealing with cosecants and cotangents, I'm going to turn them into sines and cosines. So what is cosecant? It's 1 over sine. And what is cotangent? It's cosine over sine. So y prime equals negative 2 cosine of x. Remember, this is like negative 2 over 1 over sine squared of x. I want to figure out where that equals 0. I want to figure out where that thing equals 0. Well, if you think about it, the denominator is not allowed to equal 0. Basically, wherever the numerator equals 0, the whole thing will equal 0, right? Because 0 over anything is 0. All right, so we need to figure out where negative 2 cosine of x equals 0. Well, when's that going to happen? It's going to happen if cosine of x equals 0. Where does cosine of x equal 0? Think about the unit circle. Cosine equals 0 at 90 degrees, which we write as pi over 2 radians. And it also happens at 270 degrees, which is 3 pi over 2 radians. So these are the values of x where there's going to be a horizontal tangent. So I found the x values. Now I need to figure out what the y values are. So how do I do that? I plug these numbers in for x into the original function. So what's y of pi halves? Let's go ahead and figure that out. And what is cosecant? Cosecant again is 1 over sine. So I can write cosecant as 1 over sine of pi halves plus 3. So let's simplify that a little bit. Pi halves is 90 degrees. The sine of 90 degrees is 1. Okay. So 2 times 1 is 2, plus 3 is 5. So when I plug in pi halves to the original function, it's 5. That's where there's a horizontal tangent. And what about 3 pi over 2? It would be very, very similar. I'm going to do 2 times 1 over the sine of 3 pi over 2, then add 3. Okay. Sine of 3 pi over 2, that's like 270 degrees, and the sine of 270 is negative 1. 1 divided by negative 1 is negative 1. So 2 times negative 1 is negative 2, plus 3 is just 1. So these are going to be the 2 points on the original graph, the 2 points on this curve where there's a horizontal tangent. Let's check it to make sure. Okay, so let's go ahead and type in the original graph. So 2 cosecant, so how do I do cosecant? I do 1 over sine plus 3. Now before I hit graph, I only care about this graph from 0 to 2 pi. Maybe we just scale by 1. Let's see if that does it for us. Okay, I see part of the graph, but I don't see anything over here, so I might have to change my window a little bit. So maybe instead of just going to negative 4 to 4, maybe we go negative 4 to 15. Maybe that'll do it. Oh, okay, here we go. So to me, it looks like I could draw in a horizontal tangent line about right there and about right here. So let's find the minimum of that part. What do you notice? It says the x value is 1.57. To me, it looks 1.57. If I know pi is 3.14, that looks like half of pi, or pi over 2. And the y value there is 5. What do you notice? Pi over 2, 5, right here. That was one of the points where there would be a horizontal tangent line. And the other one is 3 pi halves, comma 1. So let's see if that's right there. So I'm just going to hit trace, and I'm going to go 3 pi halves. I hit enter, and there we go. That's the top of that part of the curve. So there would be a horizontal tangent line right there. And we can confirm it if I hit second trace, go down to option 6, and I type in 3 pi over 2. What do you notice? The derivative there is 0. Do it again, and put in pi over 2 as the x value. What do you notice? The derivative there is 0, and the point has a y value of 5. That's a hard problem. It combines a lot of concepts we've been learning. So, on the back, a few more examples here, class notes. Okay, so here it says find the derivatives. So f of x equals cosine of x over 3 sine of x. You could do this using the quotient rule. There's nothing wrong with that. However, you can rewrite f of x sometimes. Well, what's cosecant? It's 1 over the sine. I'm dividing that by 3 sine of x. Well, how do you do that? How do you do fraction division? That's like saying 1 over sine divided by 3 sine of x over 1. Well, if you do keep, change, flip, you get 1 over sine of x times 1 over 3 sine of x. So you could write it like that. Okay, so that's another way I could rewrite f of x. Okay, and what does this mean? This means 1 over 3 times the sine of x squared. You could write it like that. Or you could use the quotient rule. Okay, you could just go straight in the quotient rule. Actually, I still have to use the quotient rule here because we don't know how to do something easier. All right, so let's just kind of ignore that. Sorry about that. Okay, let me actually do this on a spare sheet of paper. So here, f of x equals cosecant of x over 3 sine of x. F prime of x, let's just use quotient rule, low. Okay. D high, what's the derivative of cosecant? That's negative cosecant cotangent minus high derivative of low. So the derivative of 3 sine of x, the 3 stays, and the derivative of sine is cosine. All over low quantity squared. So let's see what happens here. Okay, so the negative I'm just going to put out front. So negative 3 times sine of x, and I'm going to rewrite cosine, or not cosine, excuse me, cosecant as 1 over sine. I'm going to turn everything into sines and cosines. Cotangent is cosine over sine. All right. Why is that nice? Because those go away. Minus cosecant, again, is 1 over sine times 3 cosine. Okay. All over, well, if I square the 3, I get 9. If I square the sine, I get sine squared. So let's see what happens there when I simplify a little bit. So what do I have? I have negative 3 cosine of x over sine of x minus another 3 cosine of x over sine of x over 9 sine squared. So notice these things have exactly the same variable on it, so I can turn that into negative 6. And I'm just going to rewrite this now as cotangent of x over 9 sine squared of x. And then you can reduce a little bit. You can say negative 2/3 cotangent of x over sine squared of x. So this is an acceptable answer. Actually, any of these are acceptable. Or if you wanted to, you could say, well, negative 2 cotangent, again, is cosine over sine, divided by 3 sine squared, oops. Negative 2 cotangent is like saying negative 2 cosine of x over sine of x divided by 3 sine squared of x over 1. Okay. What does that do? We keep the first fraction the same, change division to multiplication, and flip the other one. Okay, and you actually get an answer like this. Negative 2 cosine of x over 3 sine cubed of x. So you could write that as the answer. Or you could even get more creative, and you could do this, negative 2/3. You could take one of the cosine, or you could take that cosine over one of the sines. Think about what's in the numerator. You're still missing 2 sines. And you think about what this is going to give you. This is negative 2/3. Cosine over sine is cotangent. Okay. And 1 over sine squared is cosecant squared. So to me, what's important is you get first line answers. That's what's important to me. So like if you got it to this point, I'm okay with that. Okay. I'm just showing you there's other simplifications you could do. If you got this answer, but that was not an answer choice on multiple choice, you would just have to use some of your trig rules. Okay. Use some of your trig rules, know your reciprocal functions to simplify it into one of these other forms. Okay. So that's why I show that to you on the video, and that's why I show it to you in class. You got to get used to simplifying trig functions to make your answer match one of the possibilities. Okay, let's look at the next problem. Okay, let's look at 2. Now, 2 says g of t equals t squared cotangent of t all over 5. Well, this doesn't have any variables on it. It's just a coefficient or a constant. And there's an understood 1 in front of all this. So to make this problem much, much easier, let's just write it as 1/5 t squared times the cotangent of t. Okay. You could use quotient rule here, but there's absolutely no reason to. You just make life harder on yourself. Now what do you notice? Well, you have this thing times this thing. So to take a derivative, just use the product rule. So the product rule says take the derivative of the first. So the derivative of this thing would be 2/5 t. Okay, the 2 would come down. 2 times 1/5 is 2/5. Reduce the power by 1 times the second term, which is cotangent of t. Plus, now take the first term, 1/5 t squared, and multiply it times the derivative of cotangent. What's the derivative of cotangent? It's negative cosecant squared of that variable. So 2/5 t cotangent of t, eventually this would be a negative, minus 1/5 t squared cosecant squared of t. Okay. So this would be an acceptable answer for the derivative, or you could do some factoring. You could take out 1/5 times t, and then you would have 2 cotangent of t minus, if you took out 1/5 t, you're still missing a t, and then you need the cosecant squared of t. Okay. So you could write it like that. Now, could you do anything else? Is there any other possible answers? Yeah, there's millions of them. And what is cotangent? It's cosine over sine. What's cosecant? Cosecant's 1 over sine. So that would be 1 over sine squared. You could write it like that. You could get a common denominator here. You'd have to multiply by another sine of t over sine of t. And you could kind of do one of these things. 1/5 t, 2 cosine of t, sine of t, minus t, that coming from this piece, because you have a common denominator now of sine squared. You could do something like that. And then you could even pull the sine squared out because it applies to both terms. So you could have something like t over 5 sine squared of t times big parenthesis 2 cosine t sine t minus t. You could keep going and going and going pretty much forever, just making substitutions. Okay, so like any one of these answers, these are all equivalent to each other. Okay? To me, get to one of these 2 points. That's good enough for me. Again, this is a first line answer. Actually, that's the first line answer. Simplify it a little bit, but you don't have to keep going forever. Just realize multiple choice, you might have to keep simplifying until you get an answer that matches what you got. All right, number 3. It says h of x equals 6 cosine of x over 2x plus 1. Okay, that's a quotient. H is a quotient. So to find the derivative, I need to use quotient rule. So low d high minus high d low all over low squared. That's the first line answer. If you simplify it a little bit and see what happens. So I have 2x plus 1 times negative 6 sine of x, okay, minus, if I multiply this times this, I get 12 cosine of x, all over 2x plus 1 squared. If you keep simplifying, it's not really going to matter because, you know, you distribute each of these, you're going to get sine terms. It's not going to cancel out with any of the cosine terms. So nothing really happens if I keep simplifying. So I would probably just stop there. I'd probably just stop there. Because none of these sine terms will cancel out with that cosine term. Number 4, s of t equals 2t times the secant of t. You notice here s of t is a product. So we need to use the product rule to find the derivative. So s prime of t, the derivative of the first, 2, times the second, secant of t. And you can use parentheses if you feel more comfortable. Always plus with product rule, the first 2t times the derivative of the second. So derivative of secant of t is secant of t times the tangent of t. Okay. So that's a first line answer. If you want to simplify, can you pull out any common factors? They both have a 2. They both have a secant of t in them, so we can pull that out. So if I take out 2 secant of t, okay, well, where I took everything out, so the factor is 1, plus, okay, I still have a t left there and a tangent of t. And if you want to, you can put the argument of the trig function in a small parenthesis like that. So this is the factored form of the answer. A little bit nicer. A little bit more condensed. Okay, now number 5. Number 5 looks really hard, but it's not as hard as you think it is. So it says x squared minus 3x all over the cube root of x squared. Now before you try to use the quotient rule, let's write this differently. Let's write it as x squared minus 3x over x to the 2/3 power. Well, why do I want to do that? Because now I can take each term in the numerator and divide it by the entire denominator. But the only entire denominator is just x to the 2/3 power. Okay. Why is that more beneficial? Because I know that x squared is really the same thing as x to the 6/3. I'm going to put it in like terms. Okay. This is like 3 over 1, so I can do that. 3, and x means x to the first, which is the same thing as x to the 3/3 over this x to the 2/3. So if you keep simplifying the original function, you don't have a fraction anymore. You just have x to the 4/3 power, because 6/3 minus 2/3 is 4/3, minus 3 times x. 3/3 minus 2/3 is 1/3. Notice, by simplifying the original problem, you don't have a fraction anymore. So that's what the function is. That's another way to rewrite g of x. So when I take the derivative here, I don't have to use quotient rule at all. The 4/3 would come in front. I'd reduce that by a power. Okay. I take negative 3 times 1/3, which is negative 1. Reduce that by a power. And there we go. So that's a first line answer for the derivative. If you want to make it a little bit nicer, that's fine. So this is 4/3 x to the 1/3. I'm just going to keep that in the numerator because that's over 1. Minus 1 over x to the 2/3. Put it to the denominator and change the power to a positive exponent. So you could write it like that. Or you can write it with radicals. 4/3 times the cube root of x, or you could put that in the numerator, minus 1 over x to the 2/3, so you can write it as x to the 2/3, or you can say cube root of x squared. So that's an acceptable answer. Okay. Now, if you wanted to get a common denominator, it would probably be easiest at this stage to put an x to the 2/3 there, put an x to the 2/3 there, okay, and then put a 3 there and a 3 there. If you were to do that, what would you get? Okay, if you were to do that, you would get 4x to the 1/3 times x to the 2/3 minus 3 all over 3x to the 2/3. Well, x to the 1/3 times x to the 2/3 is x to the 3/3. Okay, so this is basically like saying 4x minus 3, x to the first power, over 3 times the cube root of x squared. So you could also write the answer like that. Okay. To me, this is good enough. You could stop there. Okay. Or you could have stopped here before you try to get a common denominator. This is just extra. If you're going to go that far, make sure you do it right. Okay. Let's try the last one here. Y equals 4 times the sine of x times the tangent of x. To me, this looks like a product. Let's just use product rule. There's the first term, there's the second term. So y prime, what's the derivative of 4 times sine of x? That would be 4 times cosine of x. That's the derivative of the first times the second. Plus the first times the derivative of the second. The derivative of tangent is secant squared. So this would be a first line answer for the derivative. You could probably make it come out nicer let's think about this. What is tangent? Tangent is like saying sine over cosine. Well, that's kind of nice because now those cosines cancel each other. Plus, we have 4 sine of x over 1. And secant is like saying 1 over cosine squared. Okay, that doesn't help so much, but let's see what we got now. So right now I got 4 sine of x plus, let me do something like this. Let's break this 1 over cosine squared up into, actually let's put one of the cosines underneath that sine and the other one by itself. Because you're still getting cosine squared. You're still getting this cosine squared. So this sine over cosine is tangent. Okay. And 1 over cosine is the same thing as saying secant. So you basically can pull a 4 out and then say sine of x plus tangent of x secant of x. Just depends. You're trying to, your real goal if you see a problem like this on multiple choice is keep going until you find an answer that matches one of the options that they give you. Okay. Like really here, they could have left the answer like this. They could have said right here 4 sine of x plus, or really right here. Okay. They probably would have taken it one more step and said 4 sine of x plus 4 sine of x secant squared of x. Okay. They would have probably, or from that point, you could have just said, take out the 4 sine of x, factor that out, and then you would get 1 plus secant squared. You would have got 1 plus secant squared from this point. So there's a lot of different options for your answer. Again, just keep simplifying until you get an answer that matches. All right, so important takeaways from this lesson. There are 6 trig functions, basic trig functions. You need to know how to take the derivatives of all of them. And then on multiple choice especially, you need to be able to apply the rules correctly and get an answer that matches one of the options. Okay. By remembering that secant equals 1 over cosine, cosecant equals 1 over sine, tangent equals sine over cosine, and cotangent equals cosine over sine. And got to remember those. Sorry for the length, but thanks for watching.